here refers to a very simple concept of reiterating a procedure. So in programming, we learn that whatever we code consists of procedures. Those procedures are basically you having the compiler, giving the compiler list of instruction and then asking them to execute it according to, for example, if there's certain conditions, right? Or based on arguments that you either throw at it or being passed around from one function to another, right? So induction here is against, like similarly we've seen, we try to see how it captures that whole mechanism of how we do our programming, right? Because everything is an iterative process. Like for example, when you have a conditional loop if else, right? So if the argument is being tested, right? You satisfy it is actually true, then it will execute the instructions, right? And then it will go back to the top and then iterate itself. So that whole process is inductive, right? But at the same time, mathematical induction is an extension of mathematical proof, because here when you do proving, remember when we prove, we have to show that it is valid. And we need to show that no matter what the value of x that we are referring to, right? Inductively, if we were to test each value, that mathematical theorem or that mathematical formula or equation will always be true, right? So that's the whole idea behind mathematical induction. So apart from that, we look at strong induction. Strong induction is also known as the second principle of mathematical induction. So just in case you're wondering, because in Kenneth Rosen's book, he always only refers to it as strong induction. But in some other books, you don't see them referring it to strong induction. They refer it to as the second principle of mathematical induction. So this second principle of mathematical induction, right, refers to this one, and this is of course the first principle of mathematical induction, right? And then we learn recursive definition. So recursive definition is how you come up with a formula based on the first solution to it, and based on that first solution, you build on top of it. So imagine it like you're building building blocks, right? The building blocks are all the same unit. That means they have the same measurement, the same size, the same configuration, the same shape, right? As you are building on top of it, it's just taking one and attaching it to another, and then keep attaching it until you make whatever structure that you want to build on. So the whole idea is that you're repeating the whole process inductively. So recursive definition is something like that. Like you say that you take 4 of those square building blocks, right? You join them together. Then on top of it, you take a single long rectangular building block. You attach it onto the left-hand side. You attach another one to the right-hand side. And then you just keep repeating the whole process over and over again. Then you get one long tower, one high tower, for example. And then recursive algorithm is similar to definition. Once you have a definition of what is the formula, the algorithm just basically works in the similar fashion for you to get all the different outcomes or output or values, as we see that later. So now, imagine that we have this infinite ladder. So what is this infinite ladder? This infinite ladder refers to this, for example, like Jack and the Beanstalk ladder, right? It's a ladder that you climb and climb and climb, and you cannot see the end of it because it's gone all the way into the sky. So probably you will just climb all the way into the next planet. Also, we do not know, right? So that's the infinity ladder. So we assume that we have this infinity ladder. And in this infinity ladder, we can then say it's possible for us to reach the first rung of that ladder. So what does this mean is that when you see something that is uncertain, right, normally we approach it slowly, isn't it? For example, when you go like jungle trekking, and then you come across a small bridge, right? Cutting that is over a stream, right? It looks old, it looks like rickety, and then we are approaching it cautiously, right? So what do? We take one step after another, right? Because we're unsure whether it's going to break, whether we are able to achieve our goal of reaching the other side. So we take the first step on that bridge. And you say, oh, okay, fine, it's stable. It's not shaking, it's not broken, right? It hasn't fallen apart. Then you take the second step. Then you take the third step, the fourth step, until you reach the last one, which we call it as N. And once you have completed that nth step, we've already reached the other end of the stream. So that's the whole idea, right? So this infinite ladder, first we have to have what we know as the basis step. That means the first step that you take. So we can reach the first rung of the ladder. That is assuming that, hey, on step number one, I call it step because rung, I think you're all sick and tired of hearing my pronunciation of it, right? And then the second step is we reach the particular rung of the ladder, then we can reach the next rung of the ladder. So at this part here, what we're trying to say is that assuming that we reach the first one, step number one, then successfully we can reach step number two, right? So step number one is what we call as the present time. So that is represented by N, right? In this case, N is 1, right? And then we say that, hey, actually, since we reached step number one, we can actually reach the second step, the second rung. So now this is actually N equals to 2. But generally, the whole concept refers to the situation of us looking at a particular rung of the ladder that is represented by N, and then we can reach the next rung. And we know that in sequence, this is N plus 1. Right? Later, we'll see the terms being interchanged between N and K. Do pay attention because though they refer to the same thing, applying or using either N or K refers to different aspects of applying mathematical induction. But generally, mathematical induction refers to the case that when we have Pn, and assuming that Pn is true, then we have to just go about proving N plus 1 or Pn plus 1 is also true. Right? So, from step number 1, we can reach the first rung, then applying the second concept, the second law, we say that we can reach the second rung. So what happens? We've taken baby steps to climb up this infinity ladder. So you have done step 1, step number 2. So what's the next assumption? The next assumption is now we are going to iterate the whole process, or inductively, we are going to do the same thing over and over again. So now at the present time, we are on step number 2. This is the present time, right? So based on number 1, we have successfully climbed rung number 2 or step number 2. And according to this concept here or this law here, we can reach number 3. That's the end goal. Finish. That's it. So now we are standing on step number 3. So if you stand on step number 3, based on this concept of N and N plus 1, it means that we can also climb up step number 4. So now we are at position of step number 4. And likewise, we are inductively repeating the whole procedure. Right? That means we are looking at going up to step number 5 and then to 6 to 7, because inductively we are just repeating it until we have reached this concept of step number K, right? And then if we are able to reach K, because we do not know K, right? Assuming that K is there because we have done the previous step inductively, then it's possible to state that of step k plus 1, right, we can also achieve it. That means we are able to attempt and successfully step on k plus 1. And that happens because previous step k has successfully been attempted as well. Right? So this is an example where it just shows you this inductive process in the first principle of mathematical induction. So now, in its formal definition, the principle or the first principle of mathematical induction state that to prove that Pn is true for all positive integers of n, we have to complete these following steps. Now, again, there's only two steps involved, or two processes or procedures. The first one is what we call as the basis step. Now, in the basis step, we just have to show that whatever we're given, the context, the theorem, the information for mathematical induction, we just have to show first thing, number one, is that P1 is true. Why? Because remember, going back to the infinity ladder, if you cannot step on the first rung, we're already unsure whether we can even climb on, we can just jump onto the second one and onwards. We won't do that. Right? So if you refer back to that bridge over the stream, right? As you're tracking, you encounter this old rickety bridge over the stream, right? And you already put your leg on the first step, and you realize that it's already broken or it's about to collapse. Would you attempt the second one? Well, some would, but then you wouldn't want to jump on the second one knowing that the first one is unsuccessful, right? So in a normal case or in a logical manner, you would not want to attempt the next one, the subsequent one, because even the first one has failed. So what does it mean? It means that whole concept of you being able to get across the river on the bridge is a failure. It's not successful. So likewise here. So inductive, the principle of mathematical induction with the basis step is to first say that you have this formula, you have this theorem, you have this theory, you have this equation, right? And you say this equation is true for all values of x. Now what you do is you first attempt the first value and you say it's all integers. Now you're dealing one, again, principle of mathematical induction only refers to integers. Some books will use something else, but keeping to the Kenneth-Rosen, here everything is just integers, right? And n cannot be a negative number. So it has to, n is a non-negative integer. So based on that, then we just test the first one. And if the first one already fails in getting the output based on that formula, then we know that no point to continue. This is already a wrong concept that you applied, or wrong formula that was given, right? So when the basis step is true, then we come to the inductive step. Now, in the inductive step, essentially, we are having to have an assumption first, right? And based on that assumption, we just have to prove the other thing is whatever we're trying to prove is also true. Yes, Tony, is there a question or something? All right, okay, sure. So then, moving back. So here, we assume PK, so that means we assume that we have reached the first rung. And why is that so? Because the basis step has already shown that, right? PK or K when equals to 1 is true for here. So assuming that this is true, now we're going to create a general concept. Now if rung number 1 is achieved, then we have to show rung number 2 can also be achieved. That way, we just inductively say that if we are able to reach rung number 2, we are able to also achieve rung number 3. And then going back to the inductive process, we say that now as rung number 3 is our first step in the procedure, and that is achievable, then we are able to reach number 4. And then it's go on and on and on until some future step on the infinity ladder, because the infinity ladder has no ending. We do not know when it will end. So we can only just try to say that, there is this concept where we are able to just say that as we move along that ladder, we are able to achieve one after another, right? So in this inductive step, we say that assuming that pk is true, that would imply pk plus 1 is also true, right? For all positive integer k. So here, k has to be from n equals to 1, 2, 3, 4, 5. Now, later on in recursion or recursive definition, n can also take the value of 0. So be careful. N can take the value of 0 or n can take the value of -1, but it's not explicitly stated as such. They say that if this is the present situation, you are the present step, n minus 1 refers to the previous step, n plus 1 refers to the following step, right, or the next step. So n minus 2 refers to the 2 previous steps. So that's why I said earlier on when we learned in set on sequence and summation, the indexing of the term is very important, especially in induction. Common mistakes I see with students is they are unable to understand that whole concept of index term, and that's why they get it wrong. So anyway, to complete the inductive step, assuming the inductive hypothesis that pk holds true for an arbitrary integer k, then we just show that k plus 1 must be true. So here is another important one which I didn't highlight, but it should be highlighted. Is that what we call as the inductive hypothesis is just to say that when we say pk is true for an arbitrary integer k, such that k is, again, remember k is a positive integer, then we just go about showing for k plus 1. Now, for climbing that infinity ladder as an example, we see that the basic steps say that we have to first test the first step. And we've shown that we can actually reach rung number 1. So then, assuming the inductive hypothesis, right, that we reach rung k, then we can also reach k plus 1. So in this case, we can also reach rung number 2. So we have completed that whole inductive step for the first iteration. And then subsequently you can say that if we can reach rung number 2, we can reach number 3. If we can reach number 3, we can reach number 4. If we can reach number 4, we can reach number 5. So hence pk implies pk plus 1 is true for all positive integers k, and we conclude by saying we can reach every rung on the ladder. So no matter whether we can see the end of it, right? Whether along the way there may be some broken steps or broken rungs, we do not know. The mathematical induction here says that we can just successfully encounter or reach each step k until the subsequent one, which is k plus 1. So some important points that we need to observe here, and this is what already I explained earlier on. We can express this whole thing as a rule of inference, because we're assuming that when we prove the basis step, which is P1, at the same time we have this assumption pk implies pk plus 1, and this is true for all values of k, that means for all integers, right? Then this would basically imply, when this is true, because we know that this is true and this is true, so true and true would then imply Pn. That means in general, when we say that you see this infinity ladder, start climbing, don't worry, you will be able to reach the top at the end. Same like Jack. You saw that huge beanstalk, he didn't know whether he could climb all the way to the top, but probably somebody applied the mathematical induction and told him, yeah, just start climbing, and you'll be able to reach all the way to the top. And he did eventually, right? So we say that once we have proven within these two procedures, or the basis step and inductive step, generally Pn, or the whole formula, the whole equation, is true. When you say that, for example, the sum of all positive integers is equals to n times n plus 1 over 2 for the first 10 sequences, for example. Yeah? In the proof by mathematical induction, we don't assume pk is true for all positive integers. We show that we assume it to be true, then pk plus 1 must also be true. That means here we do not prove for pk. We only prove for k plus 1. Why is that so? It's because the original formula is represented by this Pn. And then we did the basis step to show that P1 is true. So we say that, okay, I believe you lah when you say that x plus y equals to z, right? I believe you. So I take one integer, the first integer for x, the first integer for y, I add them together. Oh yes, it does become equals to z. So that is P1. And then we test based on that assumption of pk. I try for the next integer. So the next integer for x, the next integer for y, when I add them together, when they sum it up, it does equal to the next value of z. So we just assume that to be true, but only showing the next one. And when that is done, what we have is, we have the original formula or the original equation. You just have to apply P1, and then you just have to take k plus 1, put it into the formula, and see whether it turns out to be correct. And then you've completed this whole mathematical induction, right? So proofs by mathematical induction do not always show that we start at integer 1, right? So it can be the case where it will be some other integer, and that you'll see that later. So some instances or some examples you will encounter would say from n equals to or greater than 0. Typically, it will be n greater than 0 to indicate that it's all positive integers, right? You state it like this, or you state it as n equals to or greater than 1, right? Some cases will start with n. Some cases they'll just give it to you as n equals to 1, 2, 3, ... So to indicate that it's all positive integer until infinity, right? So do bear in mind, not all cases would refer to the basis step being P1. And this is the biggest, most common mistake where students get this question wrong. They wrongly applied, they wrongly saw the question. The question will always state for all n values where n is a natural number, then you know it starts from 0. Or you say for all values of n where n equals to 1, 2, 3 above. Or they say for all values of n as long as n is 2 or greater, equals to 2 or greater. So do pay attention to that, because if you get the basis step wrong, technically you're not allowed to move on to the inductive step in that whole proving process. So you can lose a good 15 marks for a question like this. The error there. So all this you can read on your own. This is just basically explaining in detail. I don't think we need to delve into this part. Right? So now, based on that whole concept of mathematical induction, we can see that if it is also analogous, right? Or look at another analogy of it. We say that if we have all our domino tiles, and all these domino tiles that we have are placed close to one another, with that whole goal of that if we were to tip over the first domino tile, right, this would lead to every subsequent domino tile falling and collapsing, right? And then you have this, what we call as a cascading effect, right? So the whole idea of the domino tiles is, domino theory is the cascading effect. Affects the first one, The first one will cause a second one to occur. The second one also will cause the third one to occur, blah, 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 until the end. So this whole thing is, again, is an inductive process, right? Having only to prove that you just have to knock over tile number 1, then subsequently individual tile, that means number 2, number 3 onwards, you will keep falling. So you achieve the first basis step. It will be proven that the next one can occur k plus 1, and therefore we can have all the tiles also falling, right? So we know that the first domino is knocked down, that's P1. Then we know that whenever the k domino tile is knocked over, it knocks over the subsequent tile. That's the whole idea of the domino effect, right? The domino tiles effect. That if the distance of your tile 1 and tile 2 is close enough such that if tile 1 falls, it will also cause tile 2 to be fallen as well, right? To fall as well. So that whole thing there is to refer to this. And then we can know that at the end of the day, based on this mathematical induction, we can see that safely all dominoes are knocked over. Hence, Pn is true for all positive integers of n. So if your n is 1000 tiles, if you have a whole thing, this whole thing that is made out of 1000 domino tiles, then it is still true. It's going to complete the whole process. You get 2000, 1 million, go ahead and do it, right? I think I've seen a video where they use matchstick and they burn 1 million matchsticks. It was a huge old structure that eventually caught fire, and I didn't see the basis behind that. So let us look at one example now. So for any question in trying to understand the concept behind mathematical induction?
Sir? Yeah, I don't think you can hear me.
All right. If no question, then let us look at an example. Now, this is a typical example, or the classic example for... Yes, Louis, you'd like to ask a question?
Hello, sir. Can you hear us? Sir, can you hear us, sir?
Oh, yes, I cannot hear you all, you know. Give me a second, let me just check. I can hear when the, what do you call it? Hang on. When somebody raised their hand, it did send that bell notification to me. So technically, my volume is loud enough. But I cannot hear you all. That is why I don't understand. Let me just again check the one. I think hang on, audio. Let me just check that. Using computer audio. Oh no. Okay, I know why. Headphones. It's too high tech. It gives me 5 different options for audio. AI noise cancelling output, my TV, my headphones, the laptop's phone, and that Asus bringing this. All right. Now, do ask the question again. I can hear everyone clearly.
Can you hear me, sir?
Yes, I can hear you clearly.
Okay, I can also hear myself. Can I ask a question for the basis step? So the base element can be 0 and more than that, right?
Technically, yes, it can be, normally it's a positive integer, but certain instances you will see it being from 0.
Okay.
But when we see it from 0, we still assume it as the first step or the basis step, right? It's just that the value we use when plugging it into here, right, would then be P0. But the whole concept of mathematical induction, we have to assume that that is the first step we are encountering.
Okay.
Yeah.
Also, the pk implies pk plus 1. We do not prove pk, right? We just prove pk plus 1.
Yes, because pk is given.
Okay.
Yeah.
Thank you.
You're welcome. All right. So, looking at this example here, so the question basically says that show that for all values of n, right, the summation, now there's something wrong here, isn't it? Who can tell me? I keep updating this, I keep saving it. And
There's
yet
no I at the
yes.
summation.
Yes. So it's missing the I term. So I keep updating it and I don't know why it doesn't want to show change color anyway. But so this is actually I, right? So the summation of I from I equals 1 to n is equals to n times n plus 1 over 2, right? So we know this typically as the summation of all sequence of integers. So when you say n equals to 1, 2, 3, 4, I, right? The summation of all it, let's say for the first 4 terms would be the summation of I from I equals to 1 to 4 is the same as 1 plus 2 plus 3 plus 4, right? So this is equals to 10. And then we have this general formula here. So let's say n equals to 4. So we have 4 times n plus 1 is 5. So 4 times 5 is 20 divided by 2 gives us 10, right? So now we have this formula here, and we're going to prove it to be true. Now this is a mathematical proving using mathematical induction principle. So on slide. So now when we see this given here, and again I forgot to put the I there. So our basic step is to first check what is this. Now this is missing something else. So we know that n is equals to 1, 2, 3, up, because it's already given in from here. The first starting value is 1. So the starting integer should be 1, right? So P1 equals to, on the left hand side, we have the first term, right? So the first term equals to 1, right? And then this formula itself is the same as 1 times 1 plus 1 over 2. And that is equals to 1 as well. So we have the case here as 1 equals to 1. Now this here is a bit confusing. It shouldn't be written as P1 means your answer should be only equals to 1. I'll just show you again how to do it. So black, white screen. So here we're trying to say that the summation of I from 1, screen being projected, oh yes, right, to n for I equals to n plus 1 over 2, right? So the basic step and here you're trying to prove that P1 is true, right? Would mean that we're having to look at I from 1 to 1, I, and this is equals to 1. 1 plus 1, so it's just 1. On the other side, we're just going to apply that value. So you're going to get 1 plus 1 over 2. So the whole outcome now is 1 on the left hand side, and on the right hand side is also 1. So this is true, right? So typically in mathematical induction, we're trying to show that, you know, on both sides of the equation that we have, it is true, right? Because we're going to show the step. This has its own way of doing it, isn't it? And this is saying that based on that way of doing it, we can just come up with a formula. So we're trying to say is that whole process on the left hand side is equivalent to you just applying this formula that is given on the right hand side. So we're going to prove that left equals to right. So here is where we see a lot of left hand side having to be proven to be equals to or equivalent to the right hand side. So in mathematical induction, we will see that when we are proving the k plus 1, right? So for k plus 1, many of the things that we'll be looking at is the left-hand side. We just work on it separately. Then you work on it separately on the right-hand side, ensuring that both sides of the outcome are the same. Hence, we have proven that whole concept or the whole formula using the first principle of mathematical induction. Right? So here, already proven P1. So this is done, the first basis step. Now in the inductive step, remember we need to have an inductive hypothesis. Right? So we say that assuming that Pk is true for some arbitrary integer k, so this is important to write, some arbitrary integer k. So now what we have done is we have taken all the n values here, the n variables here, and now we are converting it into k. This is what I mentioned earlier. This is where you have to be careful. N is for the general formula, k is only used when you're proving it. So do not put n in this working. I've seen students still do that, and technically we should give it 0. Sometimes I kesian because you've done so much, but still forget the first basis of it, that you have to convert n to k. Or in future when you're studying, you're like, how come suddenly question say n and suddenly I'm getting all k? This is the reason. The proving is using an arbitrary integer k. Right? So based on that conversion of n to k, we just say now the inductive hypothesis state that I from 1 to k is equivalent to k times k plus 1 over 2. Right? So this is the inductive hypothesis. So this is just rewriting the original formula in n version to the k version. Right? And then based on this assumption of pk to be true, we now have to prove for k plus 1. And what is the k plus 1? K plus 1 is you just add plus 1 to that variable. So we have for I from 1 to k plus 1 is equivalent to, and you substitute k plus 1 into k. So it will become k plus 1 times k plus 2, because it is k plus 1 plus 1, just divided by 2. So from here, we work with it separately. I would tell students to work with it separately rather than trying to do something like this, try to balance it on the left hand side and balance it on the right hand side at the same time, right? Because you're going to do working on one side, then it's easier to just work on it on one side. So let's say we assume that we're going to look at it on the left hand side, right? So this is looking at it from the left hand side, because the right hand side there's no more working to be done. That means we cannot simplify it, we cannot expand it, it's just in that form. So now our goal is on the left hand side, LHS, can we get it to look like on the right hand side? So that's the end goal here. So we know that we have this whole equation, right? And this whole equation is what? I use the white screen because I think there's not enough space there. So on our left hand side, right, and we'll see that there, we know that we say, this is the wrong one. We say that the summation of I from 1 to k plus 1, right? I. So left hand side, not right hand side. So what does this mean? This means we're looking at I from 1 plus 2 plus 3 plus dot plus the term k plus 1, right, equals to the formula earlier there, right? But we're not going to look at that yet. So here is the same as we saying k plus 1, I from 1, right? So same thing, 1 plus 2 plus 3 plus 4 dot plus the term k followed by k plus 1. True or not? You have 1 plus 2 plus 3. So this is the first term, this is the k term, this is the subsequent term, k plus 1. Then you got Also, if you want, you have k plus 2. There's some stronger mathematical induction using k plus 2. And then the previous one will be, if this is k, the previous term will be like k minus 1. And then the last two previous term will be k minus 2. Right? So you have all this. So that's why the indexing or the term indexing is very important to know. But we're only going to go up to this level here. Right? So now what is this? Who can tell me what is this?
P1.
PK.
Is it PK? Yes, exactly. This is actually PK. This whole part here is PK. Because PK is what? So this whole thing can be written as the summation of I. Why am I don't appear? I equals to 1 to k plus k plus 1. So this is what you see in some book solution. Suddenly they start give you PK. And where did PK come from? Because this is until k plus 1. But we already assume PK to be true. And this is actually PK. This is PK plus, that means the whole PK refers to the whole process of you adding all the terms until term k. And then you add the term for k plus 1 to that answer. So from PK plus k, what do we have? You know what is PK? We assume it to be true. So you don't have to prove PK. We assume it to be true because that was given to us. And that was the original formula. And then we converted it into the inductive hypothesis. So we know that this is actually k plus 1 over 2 plus k plus 1. So the whole left-hand side normally says that assuming PK to be true, what is PK? We know that PK was given with the formula k plus 1 over 2. Now we just add the term k plus 1. So likewise, if suddenly we change this to become 2. So then you have to add k plus 1 plus k plus 2. But we know PK. What is PK? PK is k plus 1 over 2. Right? Then continuing on this side, I have to erase everything here now. So we have the case now as on the left hand side. The left hand side says that it's I from 1 to k plus 1. I is the same as PK plus the term of k plus 1. This is the same as k plus 1 over 2 plus k plus 1. This is the same as k plus 1 plus 2k plus 1 over 2. If we to factorize and remove the k plus 1, we are going to get k plus 1 times k plus 2 over 2. So now this left hand side is actually the same as the one on the right hand side that was given earlier. Just this one here. So now we have proven the left hand side is equivalent or is the same as the one on the right hand side. Hence we have completed the proof. So you can say, therefore, according to the first principle of mathematical induction, this is valid. Right? I from 1 to n is equivalent to n times n plus 1 over 2. Understand? Do you need me to explain this again?
Sir,
Yes.
I just want to ask, this is something that I read from the textbook. In some cases, is it possible to prove that PK1 implies PK? Like reverse proving, like right hand side equal to left hand side in this instance lah. Upside down proving.
No, so far we don't want to do that. We don't look at that. That's not the first principle of mathematical induction. Mathematical induction solely looks pk implying pk plus 1. So
I see.
yeah, you just stick to that. All right. Whether they can be
Okay,
done,
thank
that's a different,
you.
yeah, that's a different thing. You don't need to look at or delve into it at this moment. So, conjecturing and proving correct summation formula. So this is another one. So we first need to give a hypothesis, right? And then we prove correct the formula for the sum of the first n positive odd integers, right? And then we have to prove that that formula that we have hypothesized is correct. So here, let's say we are looking at the sum of the first n positive odd integers. So what are all the odd integers? The first odd integer is 1. So 1 plus 1 itself. So it's just 1. Then the sum of the two first odd numbers will be 1 plus 3. Then you get 1 plus 3 plus 5. And then, subsequently the rest. So you get the solution as 1, 4, 16, 25, 36, 49. And hey, this is actually all squared of the nth term. That means the index value. So this is n equals to 1. This is n equals to 2. This is n equals to 3. This is n equals to 4. And this is n equals to 5. Right? So this is the first term. This is the first two terms. This is the first three terms referring to the index value. So that what you get as n equals to 3. So that's why it's 3 square. You get 9. N equals to 4. You get 4 square as 16. So we now have come up with this formula. So we have hypothesized that the sum of all the first odd integers is equals to n squared. So now we're going to go about trying to prove that this is true. We have to prove it. So we use the mathematical induction method to prove this is true. So first we have to say that the sum of all n integers, n odd integers, is equivalent to n squared. So how do we put this into a formula? We don't have to. So some questions will actually give you in this form. They'll give you the question and then they say, sure that this is true. So you know that this means like 1 plus 3 plus 5 plus 7 plus 9 until 2n plus 1. Right? So this is term Pn. This is term Pn minus 1. True or not? If you look at this, this is term number 3. So this is n equals to 3. So 3 times 3 plus 1, 2 times 3 is 6 already. 6 plus 1 is 7. So how do you get? So now this is a bit complicated here. This is 1. Oh, sorry. It should be up to here only, yeah? This refers to n plus 1. Because this is 2 times 3. 2 times 3 is 6. 6 minus 1 is 5. So if you look at term number 5, 2 times 5 is 10. 10 minus 1 is 9. 2 times 5, 10. 10 minus 1 is 9. 4, 5. Yeah, so 9. Right? And that equals to 25. Right? So that is how we get. So it's using up to here. Right? And that refers to the n value in terms of 1, 2, 3, 4, 5. Correct? This is the subsequent one. So based on this, we just go about trying to obtain n squared. So we know that the first one is true because 1 equals to 1. So 1 squared equals to 1, right? And what was the formula earlier? Remember, it was 1 plus 2, 1 plus 3 plus 5 plus plus 2n minus 1, right? So when we apply P1 refers to the first instance. The first instance is 2 times 1 minus 1. So 2 times 1 is 2. 2 minus 1 gives us 1. And then on the right hand side, remember this was n squared. N squared is what? 1 squared. 1 squared equals to 1. So that is 2. So now the inductive step, we have to give the inductive hypothesis. So what is the inductive hypothesis? We say that assuming the inductive hypothesis is true, or PK, now what is the inductive hypothesis? 1 plus 3 plus 5 plus dot dot 2k minus 1 equals to k squared. So we take the n variable and we convert it to the k variable. So then we only assume PK true. Now we prove for k plus 1. And what is k plus 1? K plus 1 is having to prove that the left hand side is equivalent to the right hand side. The right hand side is given as k plus 1 squared, because we just take the k value, we substitute as k plus 1, so we get k plus 1 squared. So now, what is on the left hand side? This part here we know is represented by pk, because that's what we showed earlier, right? What's the next term? What's the subsequent term? The subsequent term is actually 2k plus 1. Now you're wondering, how from 2k minus 1 becomes 2k plus 1? It's simple. 2k plus 1 minus 1. You take this from the n term. You put in 2k plus 1 is what? 2k plus 2 minus 1. So you get 2k plus 1. So that's that value there. So again, just to show you or to highlight, this is our pk. This is our k plus 1 term. K plus 1 term. So what is the k plus 1 term? We take the k plus 1 term, we applied into that formula earlier, which is 2k minus 1. And then we are able to get that 2k plus 1. So then, what is this? This is given already as k squared. So you have it as k squared plus, oh yeah, this, my screen suddenly like a whole dead pixel or what on the right. We have it now as pk is k squared plus k plus 1. Right? Sorry, not k plus 1, 2k plus 1, correct. So 2k plus 1 is the same as k plus 1 squared. And what is this? This is the same as our right hand side. So our right hand side now is the same as our left hand side. Right? I forgot the 2k plus 1 at the top. This is referring to the term. This is from here. So this one is an very easy one. Right? So you see that in most cases, when you already apply the inductive hypothesis to show that now you have to prove k plus 1, the right hand side is already calculated, it's already computed. So most of it would then, or the subsequent step, would then require you to just look on the left hand side to prove it to be true. If you want it to be quick, then yes, you can just do it at the same time. Just prove left hand side, and with the same equal sign, you just do it on the right hand side. But right hand side normally is already given there like that, right? So that is the example there. Maybe we can take a short break. I think it's already time now. It's 5:10, so probably can take a 5 minutes break before we show another version of this. All right then. So as we saw in the first two examples or the previous two examples, right? I stressed about having to prove the left hand side is equivalent to the right hand side, right? And that's the whole idea behind it, right? So likewise, when you encounter a question like this, now can you all hear me?
Yes, sir.
Yes,
All right, okay. So likewise, when we encounter questions like this where we're trying to prove inequality, so what it means here is we're referring to something that is in the form of x is less than y, or x is greater than y, or equals to or lesser than. Right? So here it is not equal. We're not saying that the value on the left hand side is equals to the right hand side, but the concept remains the same. Right? We're just having to show that this value of x will always be lesser than y. So you're saying that the left hand side will always be values which is lesser than the right hand side. Likewise, for the other case, when you say that the left hand side is always going to be greater than the right hand side. Right? So this is an example where we are trying to show that n is lesser than 2 to the power of n for all positive integer n. So all positive integers n, so you're trying to say is n equals to or greater than 1. So we can try first by just plugging case by case few values. So we know that the first value is 1. So we know 1 is less than 2 to the power of 1. We have 2, 2 is less than 2 to the power of 2. We have 3, 3 is less than 2 to the power of 3. Right? And then what, 4, 4 is less than 2 to the power of 4. So you know, hey, it's correct. But would it be a point where it will never be true? So that is where we need to use mathematical induction, because we can't be testing for every single value. So we're going to do it mathematically, right? Sorry, inductively. So we have now the question that states Pn is given such that n is less than 2 to the power of n. The basis step is P1 because you're looking at the value of 1. So here we've shown that 1 is less than 2 to the power of 1. So we can say that 1 is less than 2. And this is true. Right? So again, here don't confuse it like the previous example. 1 equals to 1, 2 equals to 2, some value equals to something value. I come here, it's like, oh, they're not the same value, so it's false. I've seen such instances where students have made that mistake. Forgetting that the basis step is you are referring to this. You're not trying to show that one side is equal to the other side. We're just trying to show that when you say n is less than 2 to the power of n in the first instance or in the first case, yes, indeed, 1 is less than 2. So this is true. Inductive step, we have to have our inductive hypothesis. So our inductive hypothesis refers to k is less than 2 to the power of k. And now we must show for k plus 1, assuming that pk holds true for some arbitrary positive integer k. So what is it? Straightforward. We have k less than 2 to the power of k. So what is for k? We're trying to say that k plus 1 is always going to be lesser than 2 to the power of k plus 1. Right? And that's the one here. So in this case, you notice that the left-hand side has no more proving to be done because it's just a single value there. You just plug in k plus 1. So a lot of the working now would be then we have to show for the right-hand side. So on the right-hand side, what we have to say is just that whatever we are going to get, that outcome should always be greater than k plus 1. Right? Generally how it is. You don't have to prove it is indeed, as in sense that you have to plug in values to show. Right? So we know that this is actually reverse engineering. This is using the backward reasoning method to get the solution, right? So we say that if we have k less than 2 to the power of k, we can safely say if we were to add 1 to the left hand side and 1 to the right hand side, the inequality is maintained. It's okay, yeah. So we have k plus 1 will always be lesser than 2 to the power of k plus 1. Correct or not? Because assuming pk is true, isn't it? If you assume pk is true, pk said k is always lesser than 2 to the power of k. So if I say k plus 1, k plus 1 will always be lesser than 2 to the power of k plus 1. If I say k plus 2, then it's also 2k, 2 to the power of k plus 2. Something like that. Right? Then from here, we are going to take this 1 and we say that since pk says, right, k is always lesser than, k is always lesser than 2 to the power of k, right? Therefore, we can then substitute this one to say it as lesser than 2 to the power of k plus 2 to the power of k. True or not? Because we know that 1 will always be lesser than 2 to the power of k. So from this 2 to the power of k, we got this term here. And this term here, you just have to look at its power, we factorize it, and we get it in this form. So now we know that, or we've proven, k plus 1 will always be lesser than 2 to the power of k plus 1. So in this case, what we're doing is we are still maintaining the inequality sign, but we are introducing a new term. Because based on the assumption that it will always maintain this inequality. So we take that 1, we say that 1 will always be lesser than 2 to the power of k. So if you want to put in a 2 power of k, so be it. If you want to add in another 2 to the power of k, also correct. Because the inequality sign will always be maintained. Right? But there is no purpose to add any more further because our goal is just to show for this one. Yeah. So adding in another one, then you're going to get 2k plus 2. Then no point. Right? Understand? You have a question? On this one? Understand? Huh? I think it's quite straightforward. So another example, use the mathematical induction to prove that 2 to the power of n is lesser than n factorial. Here you be careful. So you see here, that's where, like I mentioned earlier, you need to know by default what is the, you just can't use the default value of n equals to 1. Most cases it is, but like in this instance here, we're looking at n having to be equals to or greater than 4. So because of that, our basis step now is P4. No more P0. We're trying to show that this propositional function Pn will always be true in the instance of n equals to 4. That means you're just plugging in the value n equals to 4. And that is our first step. So we have it as 2 to the power of 4 equals to 16. Then we know that 16 is lesser than 4 factorial. Because this one implies 16 is lesser than 24. And we know that this is true. Right? Then for our inductive step, again, we say that we have a pk for some arbitrary integer k equals to or greater than 4. Right? Therefore, we have to prove for pk plus 1. And what is pk plus 1? We have on the left hand side 2 to the power of n. So we have now 2 to the power of k plus 1. And on the right hand side, we have so this one was not given an inductive hypothesis here is pk plus 1 says that 2 to the power of k plus 1 is lesser than k plus 1 factorial. Right? So on the left hand, so on the right hand, okay, in here it's a bit interesting because Not interesting. The same thing. The left hand side you can't do much already because it's already 2 to the power of k plus 1. You want to break it down, you're going to become 2 times 2 to the power of k, which is the same as 2k plus 2k, and there's nothing much else you can do. So now we're going to work on the right hand side. Right? So on the right hand side, we know that we have the case of now here again we're looking at reverse engineering of the factorial because we're trying to show that this is that. So we have to work backwards how to get k plus 1. So we know 2 to the power of k plus 1 is same as 2 times 2 to the power of k, right? So now I'm trying to say that this is 2 times 2 to the power of k, right? So this will always be lesser than 2 times k factorial, right? Because of the value 2 to or pk, because we say that 2 to the power of k will always be lesser than k factorial. So the inequality is maintained because now we take this value and we just put it with k factorial. So 2 times k factorial is the same as saying that it is less than taking the 2 and substituting it with k plus 1. Now, how do we bring in the k plus 1 here? It's because we know that the n has to be at least 4. So k will minimum, at the minimum level, k is 4. Here is 2 times 2. So we know that whatever term here will always be greater than 2. So the inequality is still maintained. So now we have the case of k plus 1 times k factorial. Why we want to do this is because we know in factorials, k factorial is same as k times k minus 1, k minus 2, right? Until we have times 1. At the same time, k plus 1 factorial, in looking at it in like a forward manner, is the same as we just shifting it. We say that we have k plus 1 times k minus 1, k and this whole thing is multiplied with this. And what is this whole thing here? This whole thing here is k factorial. So k plus 1 factorial is the same as k, the term k plus 1 times k factorial. So that's how we get it. So now we have proven for this inductive hypothesis, 2 to the power of k plus 1 will always be lesser than k plus 1 factorial. Right? So here it requires you to have a bit of advanced skills in your number theory. Right? So if you're a bit weak, then you have to do as many exercises as possible to really understand how we're going to prove inequality. Or else it's going to be a bit difficult for you. Yes.
Which one is always the left hand side and which one is the right hand side? Sorry, I'm very quite confused with that.
Anything that is on before your operator or your symbol is your left hand side, and whatever that is on the right hand side of
No, I mean pk is and pk plus 1. Sorry, I just
oh they don't have pk is not left hand side, pk plus 1 is not right hand side. We are, remember, pk, we're not proving anything for pk. We're only applying what we know in pk into pk plus 1. So there is no left hand side and right hand side for pk.
also the inductive hypothesis, it's not always I thought now it was like k, and now this one is k plus 1. Sorry,
okay. You see now here we assume, and we always have been assuming pk is true, so we don't do any proving for pk. So because we do not do any proving for pk, whatever information pk holds can be applied to your left hand side or to your right hand side of the equation, as long as it is being used to complete that proof for pk plus 1. So now in this inequality, we are trying to show 2 to the power of k plus 1 is lesser than k plus 1 factorial. So in this instance here, there is nothing much we can do. We cannot expand this, we cannot simplify it, so it's just left alone. Now we need to expand the right hand side. So we are going to work on the right hand side here. So in working in the right hand side, we are going to use the information that we know from pk and apply it inside here. And so you see the working here is still on the right hand side. For the earlier examples where the equality was, the right hand side is where the value is already dead. Right? You're trying to show that, you know, for all summation of I n plus 1, right? So when you use pk plus 1, this one is already just plug it in. There's nothing else you can do. So you're working on the left hand side. So in working in the left hand side to do the working for pk plus 1, that's where we apply the knowledge we know from, or the information that we know from pk. So pk is always assumed true because we want to use that information because the formula stated it is true. We accept it to be true because we just used the basis step to show, hey, it works. Yes, it's true. P1 it works, P4 it works, P5 it works. So based on that formula, we are going to now put that in, add it to the k plus 1. So in this case, we are doing it on the right hand side to show the method.
Okay, sir. Thank you.
Yeah. So don't think of pk must literally be only on the left hand side. No, not. The information where it goes into, whether left and right, it doesn't matter. But you know that you can only apply the information or the form only from pk. So k plus 1 is what we are proving only. All right. So moving on.
Yes, sir.
Okay. So proving divisibility results. So here it's the same thing. We use mathematical induction to prove that for the case of n, this is n cube, n cube minus 3, this is divisible by integer 3. For every positive integer n. So we are trying to say that 3 divides n to the power of 3 minus n for all values of n greater than 0 or equals to 1 and above. So here the basis step is P1. So what is P1? P1 is 1 to the power of 3 minus 1. We get 0. So we know that 3 divides 0. So the basis step is true. For the inductive step, now we assume pk holds true. And what is pk? Pk says that k to the power of 3 minus k is indeed divisible by 3. So we are trying to show now for pk plus 1. And the inductive hypothesis states that 3 divides k cubed minus k. So for k plus 1, what is the case? That again, now remember this is still 3, it's not k plus 1, so it is 4. It's still 3 divides k plus 1 cubed minus k plus 1. So it has to be in that form of this, right? K plus 1 cubed minus k plus 1. Now in this whole case here, now we have to focus on this one here. So this one here is given here like this. So now in this case here, there is no left hand side or right hand side. There is no inequality, there is no equality. We are only trying to say that now we have a general term. This general term is k plus 1 minus k plus 1. Whatever the value there, should we be able to be divided by 3, or is a multiple of 3. And that is us having to prove that based on pk. And pk says that k to the power of 3 minus k is divisible by 3. So for k plus 1 to the power of 3 minus k plus 1 is the same as this one. then plus this. When we arrange it, we get it like this, right? So now when we get it in this form, right, our goal here is to show that this individual terms is indeed divisible by that integer, because if you know your number theory well, every term that is divisible by 3 is indeed divisible, is a multiple of 3. So we know that this one is fine. Right? 3 times k squared plus k is a multiple of 3. So that term is fine. Now we have to look at this term here. K cubed minus k. Now, based on the inductive hypothesis here, pk is said to be what? K cubed minus k is indeed divisible by 3. So this one, the information for you to prove that it is indeed a multiple of 3 comes from your pk. This one, you just have to explain. Since this is a multiple of 3, hence it is divisible by 3. Therefore, your k plus 1 cubed minus k plus 1 is indeed also divisible by 3. Hence, we have completed. Yes.
The k cubed minus k, is it k cubed minus k or is it k times 3 minus k?
This is a cube.
The one next to IE. Oh, it's a cube,
Yeah.
okay.
Yeah, I already stated here. This is cube. It's not 3, because I already changed it, but this keep doing it on its own. That's why you notice that this is 1 to the power of 3. Right? It's n cube minus 3. All right, so that is that. This one is using a subset. It's almost really 6. I think I want to skip this one. This one I will hardly ask, but just to very quickly go through this. Now, in the case of trying to do mathematical induction for subset, use mathematical induction to show that if S is a finite set with n elements, where n is a non-negative integer. Now remember, n can never be a negative integer because you either have a null set, 0, or 1 set, 2 sets, 3 sets. Or from one individual set A, we can only break it down to null set, right? A subset of 1 element, a subset of 2 elements, right? A subset of 3 elements, so on and so forth, until n elements of the set. So always remember, when proving for subsets or proving for sets, it is always given that it is a non-negative integer, right? And here it can start from 0, not 1. So then S would have to the power of n subset. So this is the formula, isn't it? That you have given the set S such that A is an element of S, right? We know that the total number of subset is, or your power set is 2 to the power of n, right? The number of elements in that set S. So we're trying to use mathematical induction to prove it. So here it's a bit different. Here there is no equation and all. Here we're trying to base on the building block of set. So our basis step says that P0 is true. What is P0? Null set. So we say that the empty set only itself is indeed a subset. You know, isn't it? A subset of n can also be the empty set. And at the same time, 2 to the power of 0 equals 1. So we know that a null set is itself a set, so it is 1. And 2 to the power of 0 equals to 1. So it is indeed true. So for your inductive step, here where it becomes a bit different, we have to show that from that original set, we have a subset, right? And that one is then, see whether I can make it bigger. Can make the screen bigger because I can't really see the text there, it's a bit too small. But anyway, so now we have to say that we have a set T, and then the T has k plus 1 elements, right? And that set T would then consist of the original set S and this new element A, because A belongs to T. T say that I have one extra element, right? And Therefore, to get S is the same as you take that set T and then you minus that one element. And we know that the cardinality of T is K, right? So we break it down to the original S and that T with the additional element A, and then you have the original set for S, which is the T and X with that additional element A there. So that means that you are looking at A being either one element, one element or more than one element, right? So by inductive hypothesis, you show that it indeed has two subsets, right? Or 2 to the power of K subsets, since there are two subsets of T for each subset of S, and the number of subsets of T is the same as 2 to the power of K. Hence, we have 2 times 2 to the power of K, or 2 to the power of K plus 1. And we've completed that proof here, because we're trying to show, in this case, if it's if PS equals to 2 to the power of N, PS plus one more additional element is the same, should have 2 to the power of N plus 1 subsets as well, right? So that is that there. So proof for mathematical induction, you can read this on your own. I think this is just basically looking at how you just write it formally. We have the basis step, then we have our inductive step, and then having to go about writing left and right and this and that, completing it, and then you just have to say by mathematical induction, we have proven that Pn is true for all integers of n, such that n equals 2 or greater than p. So now, strong induction now. What is strong induction? Strong induction is the second principle of mathematical induction. And in the second principle of mathematical induction, we say that we have to prove Pn is true for all positive integer n, where Pn is a propositional function. Again, and what is that propositional function? Is now it sounds like totally different than the first one, but what it basically says is that first we verify that the proposition P1 is true, right? And then we say that show that the conditional statement of P1 and P2 and Pn and Pk is true, therefore implies Pk plus 1 is true for all positive integer k. So this is called the second principle of mathematical induction. Now, does it look different than the first principle of mathematical induction? Is there anything else that is different? Now, it still has its... What is it then?
You have to prove of several steps before you can prove Pk plus 1.
Yes, that is true. All right. So in this case, it's called a strong induction is because in the earlier case and in generally mathematical induction, we just only have to assume that you are able to step on the first rung. So in the first principle of mathematical induction, and going back to the stream analogy, if you see that bridge across the stream, that rickety old bridge, and you took the first step, right, and it didn't collapse, it didn't break, technically by mathematical induction, you say, oh, you can safely cross the river. Because why? Step 1 is achievable, step 2 is achievable, then step 3 is achievable, then step 4, so on and so forth until k plus 1. And by the time you reach k plus 1, you're already the other side of the stream. Now, strong induction says, no. That doesn't work that way. I'm not confident just with stepping across the first step, right, along the river is sufficient in reaching the other side. So you say that I now want to ensure that when I take the first step, it is successful. And at the same time, if I take the second step, it's also successful. And if I take the third step, it is successful. So what it means is, if I take the first 3 steps here, it means that I'm almost certain that the subsequent steps are also achievable. I can attempt them successfully. So that's where the strong term comes from. One step is not enough to convince you to be able to cross the river, across the stream on that bridge. You need a few of it to work first. So, but this whole concept is still an extension of the first one, because when you prove the first three is achievable in the infinite ladder example, now first three, or let's say the first four you have attempted according to this second principle of mathematical induction, the subsequent four steps are also achievable. Which means now that when we reach 1, 2, 3, 4, we safely say we can reach 5, 6, 7, 8. And what is step number 9? If 9 is our k plus 1, that k plus 1 automatically is achievable, because why? I just have to look at the previous 3 steps. Let's say the previous 4 steps. The previous 4 steps refers to this one. That one refers to the previous 4 steps to the first one that we have attempted. So this is where we look at it back to that original principle of k plus 1. This is assuming to be k. The first 4 steps are taken. So you end up with 5. You prove for 5, you prove for 6, you prove for 7, you prove for 8. It works. Then when you reach this level here, k plus 1, certainly you'll be able to reach it. Because why? Because this is saying that I'm going to refer back from the k plus 1, I'm going to refer back to the pk. Pk is a list of this. This says that the 5th step I was able to reach. That 5th step, if you again retrospectively apply the k plus 1 to look at the pk, pk says that I reached the first one. Right? So that's where you see P1 holds true. Still going back to the first step. Because step 1, you have proven. Then you prove for a successive number of steps. Then you say this group would then say this whole thing is our pk. And then the next set of 4 steps will be our k plus 1. And that is our pk in the previous 4. So if this is our k plus 1, the previous step is the k. Right? So it just does that. So rather than, so think of it like a shifting frame. When you learn so your frame can be either a size of 1, so you're only going up 1 step at a time, or that size of your frame is bigger than that. So in this case, it's 4. So you prove for the first 4. Then the subsequent 4, the following 4, and all is inductively proven to be true as well. So we can reach the first rung of the ladder. For every integer k, if we reach the first k rung, then we can reach the k plus 1 rung. So here, the first k rungs means the first 5, the first 4. So that's why we have k4. And then subsequently, we can reach the k plus 1 rung. So in this case, if this is 4, that means we can reach rung number 5. Likewise, rung number 6 is also achievable. Why? Because we know we've already proven for 5. So the previous 4 is going to be 5, 4, 3, 2. So 6 is also achievable. What about 7? 7 is the same thing. 8 is the same thing. Now, once we reach 8, this 4 just has to refer to this previous 4 that was proven earlier. Then, the next 4 is also the same case. I look at the first 4 and I see twice of it will give me this. Then the next 4 up there is based on 3 times of you doing that inductive process from the first 4 here. So this one is you inductively proving, or round 1 of proving. This is round 2. This is round 3. So 3 times inductively you've proven from the basis step or the first 4, like the one here, right? So that's that whole idea there. Like, there's everything such a mess in color. So to conclude that we can reach every rung by strong induction in this example here, we show that we already shown P1 is true. Inductively, we assume that P1 and P2 until Pk holds true for an arbitrary integer k, and we just show that k plus 1 must also be true. Right? And how do we do that? We see the next one. So suppose we can reach the first rung and the second rung of the infinite ladder, then we know that we can reach a certain rung or certain step in the case that it is now 2 rungs higher. So we prove that we can reach every rung in such manner. So that is going back to the original mathematical induction. You understand that? So you have your steps. So this is step number 1. This is step number 2. This is step number 3. This is step number 4. So on and so forth. This is step shown for step number 1. Then we just assume that pk2 we prove for your second step. So we know that we can reach the second step. Right? Now once we reach the second step, what is step number 3? Step number 3, we know that successfully we have achieved it because inductively we have already shown for number 1 and number 2. So number 3 is obtained. So if number 3 is obtained, then number 4 can also be obtained because the first principle says previous one true, pk plus 1 should be true. Then we show 4 is true. Now we have this collection already of first 4. So now you have picked a random number. Step number 6. What does 6 say? Number 6, we are unsure because we haven't reached number 6 yet, but we're trying to say now 6 is k plus 1. Can we achieve it? Yes. Why? Do we know for 5? Step number 5, we do not know. But we know that before 5, we have proven for the first 4. So this first 4, if it's successful, the next 4 is successful. So even if I randomly just choose the step number 8, I don't have to show 7 has been achieved, 6 has been achieved, 5 has been achieved. No. I just base on this inductive process where I've proven 1, 2, 3, 4 has been achieved. So if that first 4 is achievable, then number 8 is achievable because by right 7 is achievable because in this case this is achievable. Why? Because 6 is achievable through the case of 2 being achievable, then 5 is achievable through 1. Hence, this one is also achievable because it meant to say that the first 4 are also achievable, right? So, we reach the first step. Inductive hypothesis says that we reach the first k rungs for any k equals or greater than 2. We reach the k plus 1 rung since we can reach the k minus 1 rung by the inductive hypothesis. So therefore, we have reached all the rungs of the ladder. So here, the k minus 1 refers to what? If this is your number 8, this is number 9. So 9 refers to your k plus 1, 8 refers to your k, and everything else here is your k minus 1. Alright? In a group, in this instance, I'm using 4. So in the group of 4. Right? You can always use strong induction to prove instead of using the first principle. But if there is no need for us to show a very strong proof, then we just keep to the first principle of mathematical induction. The principle of mathematical induction, strong induction, as well as well-ordering properties are all equivalent. Now, well-ordering properties is not in the syllabus yet. It's expected to be only approved for next year. So, or else then you have more headache once you learn that. Sometimes it's clear how to proceed using one of the three methods, but not the two. So let us look at an example here. So let's say we have the case that n is an integer greater than 1, and n can be written as the product of prime numbers. We know that, isn't it? So we say that if n is an integer greater than 1, so we know that n is equals to or greater than 2, right? It is a product of prime numbers. So what is the first basis step? We know for P2, because the first integer n has to be 2. So we know that 2 is indeed itself a prime number, so 2 is derived from a prime number, a product of prime number. So this is probably what, 2 to the power 1 times 2 to the power 0, or something like that, right? So the basis step is true. In the inductive step, we have the case of Pj is true for all integers of j such that, now j has a minimum value because it starts from integer 2, so 2, until a certain number of provings we need to do. So this is where we have the first rung, the second rung, the third rung. So we need to just prove for first few. If we can prove for the first few, then we don't have to do for the rest. So j would take a value until k, right? And here they didn't mention, isn't it? So to show the subsequent one, you all have to do under the assumption is that up to this value of k, that means if you say that the integer 2, 3, 4, and 5 is proven to be true for the inductive hypothesis that it is a product of prime numbers, then k plus 1 will be the integer 6, right? So if k plus 1 is a prime number, then we assume that k plus 1, pk plus 1 is true, right? So otherwise, k plus 1 is a composite number, integer, that can be written as the product of two positive integers, a and b, such that that integer a is at least 2, because you have two integers, both have to, one has to be bigger than the other. So a, b is the greater one than a, and this whatever integer has to be less than k plus 1. And why is that so? Because when that integer you're looking at is indeed a prime number, then it is also true for pk plus 1, isn't it? Or pk, that any integer greater than 2 can be obtained from the product of prime numbers. Now, when that number is not a prime number, we have to look at case 2. Case 2 says that any composite number can be obtained in this manner, a and b. A is a prime number, b is also a prime number. Product of two positive integers. Oh, sorry, not prime number, it's a positive integer. Composite can be written as a product of two positive integers, sorry. And that positive integer must be at least 2 and lesser than that number, which is the prime number, of course, and another integer b. So by inductive hypothesis, a and b can be written as the product of prime numbers, and therefore k plus 1 can also be written as the product of these prime numbers, right? So hence it's been shown that every integer greater than 1 can be written as the product of prime numbers. So when you have these two integers, these themselves, by the inductive hypothesis, they say that pj is true for all integers j such that j is at least 2 and equals to or greater than k, or at most k. So at least 2 and at most k, and then we know that a and b are also a product of such prime numbers. Hence, k plus 1 can also be written as the product of those prime numbers, right? So that is that. Don't worry about too much on this one. It's a bit too general. This is where it's very important and it becomes interesting. Now, prove that every amount of postage of 12 cents or more can be formed just using 4 cents and 5 cents stamp. So let's say we Pn to be the proposition that postage of n cents can be formed using 4 cents and 5 cents stamps. So you have the case of the basis step. So in this case, all we've seen previously for the strong induction indicated that we have to use only P1 or Pn. Like they said earlier, n equals to 2. So you look at P2. Not necessarily. Strong induction can also be for that series of steps that needs to be assumed to be true. And once that is true, our inductive step becomes a bit more clear. So like in this example here, drink. So in this example here, you need to show that every amount of postage at 12 cents or more can be formed using just 4 cents and 5 cents stamp. So now they say any amount of postage above 12. Why they pick 12? Why didn't pick some other value? So let's just see why. So we have the scenario of us having a 4 cent stamp and a 5 cent stamp. And we having our total postage, right? So if let's say we have only one 4 cent stamp in hand, what is the total postage? Or total amount will be 4 cents only, right? Now, if we only have one 5 cent stamp, what's the total postage we can get? We only get 5 cents postage. Now, if I have only two 4 cent stamp postage, what do we have? I only have 8, right? If I have one of 4 and one of 5, if I use a 4 cent stamp and a 5 cent stamp, this will give us a postage of 9. Now, if I get a postage using two 5 cent stamps, it will be 10. Right? So when you see this sequence of postages, right? Can you ever get a postage of 3 cents, a total of 3 cents? No. Can you get a postage where it's 6 cents? It's not possible, isn't it? Because it's either going to be just one 4 cents or one 5 cents. And that will give us 9. What about 7? There's no way. It has to be 4 plus 3 or 5 plus 2. Right? So what about 11 now? 11 is also not possible. So what about, so when we stop here, what we see is there is 1 0 0 1 1 1 2 0 0 2, and now we come to the third combination, because this is a combination of 1 0 0 1 1 1 2 0 0 2. Now we have 2 2. 2 2 gives us what? Sorry, shouldn't be 2 2. This is actually 3 0. I'm going by minimum value. So 3 or 4 cent stamps will give us a value of 12 cents postage. What about postage of 13? Can we get 13? 13 is 5 plus 8, isn't it? So 2 of 4, 1 of 5 would give us 13. What about 14? 14 is 1 of 4 and 2 of 5 to give us 10 plus 4. And you got 14 cents of postage. And 15 cents is having us to just take out 3 5 cent stamp to give us 15. And then, what is 16? How do we get the postage of 16?
4 or 4-cent stamp.
Yes, correct. So you have a 4 cents, you have a 5 cents. 16 is obtained by getting 4 of 16. 4 or 4 cents to give us 16. How do we get 17? 17 is we just add one more 4-cent stamp to where? Here. Likewise, just like what your friend said just now. How do we get 16? We just add one 4-cent stamp to this fellow here, which means adding 3 plus 1 to get 4. 4 or 4 cents is 16. If I add one more 4-cent stamp to this, I will get 17. How is this 17? Now this is 3 plus 1. How do I get 18? I just add one more 4-cent stamp to this one here. So this is 2 and 2 to give us 18. How do I get 19? Again, I just add one more 4-cent stamp to the one here. So I get 1 and 3. 15 plus 4, 19. So after this, it is guaranteed any combination of postage can be made or can be achieved by just adding one more 4-cent step to this 4. So that is why you have to first prove these 4 steps. Postage of 12, 13, 14, 15. After that, any of it can be just by adding one 4-cent stamp, 2 4-cent stamp. All this is adding just one 4-cent stamp. If I add one more additional 4-cent stamp, it will refer to 16 plus 4. So I get 20. 21 is just adding another 4-cent stamp to this guy here. So it's 4 and 1. Now it becomes 5 and 0. Right? Understand? So this is the whole strong induction where first we prove a series of Pn's, and then inductively, this is the Pk plus 1. Those Pk plus 1 is to show that these values are achievable based on the previous 4 steps. So 19 is not obtained from 18. Neither is obtained from 17. Neither is obtained from 16. 19 is obtained from a k minus 3. That is our k. K minus 3 refers to this. This is our k minus 3 step. Right? Going forward, then it will be k plus 4. This is our k. 1, 2, 3, 4. If this is now our present value, this is k. This refers to k minus 3, not k minus 4. You see that in the slide here. Good job. Our basis have shown for 4 successive values, and for any value after this, just use the minimum 4. Now, this kind of question can be for postage or stamps. It can be combination of cents. Let's say I have a 5 cents coin. I have a like US, they use dime. So you have a 6 cents value stamp, right? A nickel and all that. I don't want the value. Then always look at the smaller one, right? So if this says 5 cents, then you have to show a successive increment of value 5 times. In this instance here, because you're using 4 cents, we are looking at 4 successive steps. If we want to use for 6, then you have to show for 6 successive steps. But this is unnecessary because normally we use the smaller value. No point look at the bigger value. It can also be for combination of notes, or let's say voucher. You got Pakistan voucher. Pakistan voucher usually 10 or 20. 20 ringgit or 10 ringgit Pakistan voucher. How many different total amount that you must spend for you to use this voucher? So here, no point looking at 20 because 20 is actually a multiple of 10, for example, right? So you might as well look at 10 successive postages you can get, and the subsequent one, I mean, total amount you can spend, and then the subsequent value amount is just by adding one more, 10 you get voucher. So that's the whole concept there. So the inductive hypothesis, yes.
Can you explain again? So like 12 to 15 is PK, then like 16 is PK plus 1, then PK minus 3 is 15, right?
Yeah.
So where would the K would be 18, right? Is it?
Well, you see, now in this basis step, this is not PK, this is you applying the values, you're putting in the values, right? So going back to, see, you go back and look at the question originally, so all this. Now the question, just don't look at the solution yet, just look at the question so you don't get confused. Question says that prove that every amount of postage, 12 cents or more, can be formed by using a 4-cent or 5-cent stamp, right? So now the basis step is what? I have to show that the first round, the second round, the third round, we do not know how many. So, but we know that because the question says just using 4 and 5 cents. So in this case, can be formed using 4 and 5 cents. So we show that the first one is 12 because they say minimum 12, postage of 12 and more. And then when we look at 13, it's also can be obtained from a 4 or 5 cent stamp. And then for 14, again, it's obtainable from 4 and 5. And then lastly, 15. Now, why we stop here is because 16 is a redundant step, as in we just have to redo this one. That means inductively, we just repeat this process here. And also because we are trying to just say that I'm going to use additional, I'm just going to just add one more 4 cents and just add another one more 4 cent step. So that's why we show the first 4 postages. That is basis. It's not PK. So now we come to the PK part. So in the inductive hypothesis, we say that we have this value of PK. Now this PK is actually a range of values. So this is J. And this J holds true such that J is at least a postage of 12 and until the value of K, right? Where K must be equals to or greater than 15. So here is where you defined your PK. So yes, this is indeed PK, but you cannot look at it as the value of your PN or your PK. Don't look at it that way. Only in the inductive step, then we define what is your PK. Okay? Got it?
Okay, so
Yeah. So this is just for you to show these values, these postages are true. So there is nothing got to do yet because PK is not defined, PN is not defined. They didn't define anything, just says the postages are given like that. So this one is a given because when you're using this step, it is it's sequential, right? Because they're integers. So you're looking at one integer after another. So you should be able to find that number 12, 13, 14, 15 can be obtained. Because the question is already given like that. The question asks you, show that it can be 10. Cannot, because earlier when we look at the table, we saw that 11 is not achievable. So what happens is, it will give you a total that is inconsistent, right? And then suddenly you notice that it will increment by 1. 12, 13, 14, 15. So some other examples, so you see the same thing. It will give you all weird values and suddenly it will increment by 1. 24, 25, 26, 27, 29. Then you know that is that combination that you have to start. Understand? Why? Because the previous values cannot be obtained. We no guarantee because we know 11 cannot be ever obtained. So we cannot use strong induction to show before the value of 12. So then in this part here, we say that now we have this range of values from 12 to K. K is actually taking 15, right? And assuming the inductive hypothesis, now we have to show for pk plus 1. Now what is pk plus 1? pk plus 1 says that the next subsequent step after 15 can be obtained by adding one force stamp to that k minus 3 position. And that's how I showed you. How do you get
Oh, I get it now. Thank you, sir.
yes. So how do you get 16? 16 is just by looking at k minus 3 step, and that k minus 3 is 12. So 12 plus 4 step. Now you know. So it keeps to this frame. That frame can be any size n. Oh, sorry, size j. Here it's referring to the j. But the subsequent step, which is all k plus 1, is not an individual value. The individual value is just just one instance of the k plus 1. That one is referring to the previous whatever step. In this case, it's k minus 3, which is 4 steps behind, because the first 4 is proven. So that's why I said 20-cent stamp can be obtained from adding 2 4-cent stamp to 12. Was it 12? 2 4-cent, yeah, correct. 8. So 24 cents postage can be obtained by adding 3 4-cent stamp to k minus 3, which is 4 cents postage. Understand? So this is the whole concept, and this is the only thing that actually applies or usually we use for strong induction questions, right? So the concept you need to understand. To understand, go back and read until you get it right, because it's not hard, because it took me a while to understand it, but later I found out that it's just quite straightforward. So this is using
Sir,
yeah.
if I
Yes.
can, if I read the slides, I will be able to understand it, right? Like, okay.
Should be able to, I mean, this part of reading the slide, because the inductive blah 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 k equals or greater than 15. Using inductive hypothesis, k minus 3 refers to the other one. K minus 3 is equals to or greater than 12 because that's the minimum value. So k will either take a value of 12, k minus 3 takes a value of 12, k minus 3 takes a value of 13, k minus 3 takes a value of 14 or 15 because there are 4 positions only, referring to your k plus 1. So I say k plus 1 should never ever look at it as an individual value. It's just one instance of the subsequent 4 steps. So these 4 steps would say this is k plus 1, this is k plus 1,